Dear friends, one of the previous classes we have discussed about voids. When spherical shaped spheres or particles, it may be atoms, molecules or ions, may be arranged in a cube. Definitely there will be vacant spaces or voids. That voids can be triangular void, tetrahedral void, octahedral void or cubic void. But today we are going to identify the positions of tetrahedral and octahedral void. What is a tetrahedral void? When we have discussed about hexagonal close packing, where in a layer 3 particles are present, and at the center of or at the intersection of these two spherical particles you can see a void, that is triangular void. And when this gap or triangular void is capped with a particle from the upper layer, you will get a tetrahedral void between these 4 particles. You have to draw a line from the center of the white particle, to center of this red particle, this red and this red. Then connect these 3. Then you will get a tetrahedral shaped. First a triangle at the base between 3 red particles, and at the center we have a white particle. When it is connected, you will get a tetrahedral, that is tetrahedral void. In CCP arrangement, in a layer you have 3 particles like this to get a triangular void, and in the upper layer you have 3 particles like this, one here and one here. Between these 6 layers you have a void here. The shape is a triangle here, and connecting between them. Then you will get a triangle like this and a triangle like this, connecting these two, that is the square plane of the octahedron. Then you have to connect this and this. Then you will get an octahedral void at the center. Since octahedral void is formed between 4 particles and octahedral void between 6 particles, definitely the space or the void is bigger in size. Octahedral void is bigger in size than tetrahedral void. Now we have to see in a cubic system how they can be located. Consider an FCC arrangement of particles. FCC arrangement of particles. In FCC arrangement, particles are present at the corners as well as at the face centers. 1, 2, 3, 4, 5, 6, 7, 8. It is not 8 unit cells, it is a single unit cell, and divided like this: front face, back face, top face, bottom face, left face center, right face center. In order to locate tetrahedral void, you should have a triangle at the base and one at the top. For this purpose, you have to identify a corner, a single corner, and 3 adjacent face centers. Suppose you are taking this one. This is a corner particle. What are the adjacent face centers? Left face center, that is 1, front face center, that is 2, and bottom face center, that is 3. You can connect them. One to two, two to three. This is the base of the tetrahedron, that is a triangle. From this you can connect to this point, to this point and this point. Then you will get a void between them. Tetrahedral void can be seen here. You can see a tetrahedral void here. In that tetrahedral void you can arrange particles. So you will place a particle at the tetrahedral void here. So for each corner you can create a tetrahedral void. For each corner you can have tetrahedral voids. So here is a question: how many particles are there in this cube? How many particles are there in this cube? This cube is arranged in FCC, so particles are 4 in number. 1 by 8, 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 1 by 8. 8 into 1 by 8 plus half, 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 half. 1 half here, 1 half here. 6 into half. Totally 4 particles. How many tetrahedral voids can be drawn here? Around this corner we have one tetrahedral. Around this corner also you can make another tetrahedral void. Again around this corner, this corner. So for every corner you can create one tetrahedral void. So you can have 8 tetrahedral voids since we have 8 corners. Since we have 8 corners and we are able to create tetrahedral voids for every corner, it is possible to draw 8 tetrahedral voids. So if particle is 4, tetrahedral void is 8. If particle is 4, tetrahedral void is 8. Now suppose you have to locate octahedral void. For an octahedral void, you have to keep 6 particles around that void. 3 in the lower layer and 3 in the upper layer. Again you have to consider an FCC arrangement like this. 8 particles at the corners and each particle on every face center. This is FCC arrangement, and here you can see a void at the body center. This void, that is an octahedral void. Why it is an octahedral void? Because this void is surrounded by 6 particles. You can draw a square from here to here, then here and here, then square is ready. A particle at the top and a particle at the bottom. So connect them also. 1, 2, third corner, fourth corner. From the bottom particle also you have to connect to all the corners. Okay. Then you can see a octahedral space here. At the center of this octahedron you can place a particle, then it is octahedral void. For a single cube you have only one body center. That body center is an octahedral void if the arrangement is FCC. If arrangement is simple cubic or body centered, this is not an octahedral void. For an FCC arrangement you can have an octahedral void here. Now one more position you can locate. Where it is? You have to consider this edge center. In this edge center you have 6 particles. You have 6 particles around it. Where are the 6 particles? you can see a particle here, then 1. You can see a particle here, that is 2, 3, 2, 3, here 4. Now you have 2 more particles. This is a single cube, single unit cell. But in crystal lattice, you can see unit cell here, unit cell in the upper side, right side, everywhere. So you can expect a particle here at the top face center, just like this particle, just like this particle. You have a particle here in this cube. Just like a particle like this, you can have a particle here also. So this space is, this position is surrounded by 8 particles. Then you can draw the cube. How to draw the cube? See, not cube, a octahedral, square. This is our square. One particle at the top to this corner, 1, 2, 3 and 4. In the same way, from here. So that edge center is also an octahedral void. Since each edge center is surrounded by 6 particles, that will develop an octahedral void. How many octahedral voids can be seen in this unit cell? At the body center, you have 1 unit cell, 1 plus each edge center. What are edge centers? 1 is here, 1 is here, 1 is here, 1 is here, next one, this is 1, another one, next one, here 1, here 1 and here 1. You can see 12 edges, but each edge is shared by 4 unit cells. So contribution to this unit cell is 1 by 4. So 1 plus 12 by 4, 1 plus 3 equal to 4. So totally we have 4 octahedral voids, 1 at the body center and 12 at the edge centers, but contribution is only 1 by 4, totally 4 octahedral voids. So we have 4 particles here. Particles means the constituent particles arranged in FCC. You never look into the octahedral voids, that is another case. Here the particle is the rose colored one, which are present in FCC. They are 4 in number. So you have 4 particles, then octahedral void is also 4. If you have 4 particles, tetrahedral void was 8. So generally you can see that for n particles, tetrahedral void equal to 2n and octahedral void equal to n. Based on this fundamental relation, you have to solve many problems. This is the way in which tetrahedral and octahedral voids can be located. In an ionic crystal, we have 2 kinds of constituent particles. They are cations and anions. Cations are positively charged and anions are negatively charged. How an anion is formed? Anion is definitely formed by the addition of extra electrons to parent atom, and when an electron is removed from parent atom, you will get cation. So you have already the idea that anions are always bigger than parent atoms and cations are smaller than parent atoms. So usually in ionic crystals, what we can see is that anions which are in bigger size can be used for close packing. And cations, which are smaller size, can occupy the octahedral void. Once again, the anions having negative charge is bigger in size, so they can be arranged in FCC, CCP or in BCC. When these bigger particles are arranged in a cube in FCC, CCP or in BCC, definitely there will be vacant spaces. It can be tetrahedral or octahedral void. If the anion is smaller one, void will be also small. If anion is bigger one, void will be bigger one. To that void, depending on the size, we can arrange cations. So, from the size of cation to anion, radius of cation by radius of anion, this is called a radius ratio. From this ratio of radius of cation to radius of anion, we can predict the structural arrangement in crystals. If this radius ratio is 0.155 to 0.225, then coordination number is 3. Coordination number means number of touching spheres 3. Arrangement is triagonal planar and example is B2O3. That is not very common. If cation is somewhat bigger, if size of the cation increases, since R plus is in numerator, definitely radius ratio increases, and 0.225 to 0.414, it is a higher value, then coordination number is 4, then arrangement is tetrahedral. Example, ZNS and CDS. ZNS is also known as zinc blende. So the structure is also known as zinc blende structure. What is the structure of CDS? That is zinc blende structure. But what is the arrangement of CDS? That is tetrahedral arrangement. Arrangement is tetrahedral, but structure is zinc blende structure, just like a zinc blende. If cation is again size increases, for a bigger cation you will get higher value 0.414 to 0.732. Coordination number again increases to 6 and arrangement is octahedral. Then there you can see octahedral void and particles can be arranged in octahedral voids. Then it is octahedral arrangement, just like NaCl, KCl, KBr, AgCl. Here the base is NaCl. NaCl is also known as rock salt. So the structure is called rock salt structure. Rock salt structure, KCl, KBr, AgCl, all of them have rock salt structure with coordination number of 6. If cation again become bigger, then again ratio increases to 0.7 up to 1. 1 means cation and anion are same size. Then higher coordination number of 8 is possible. That is possible in BCC arrangement, which is also known as cubic arrangement. Cesium chloride and calcium sulfide are examples. This structure is also known as cesium chloride structure. So arrangement is zinc blende or rock salt or cesium chloride. Otherwise tetrahedral, octahedral or cubic. This is the radius ratio rule. Based on this radius ratio, you can also identify the structural arrangement. In question, you can be asked that in an ionic crystal of AB, radius of cation is this much and anion is this much. Identify the structure to which it belongs. Then definitely you can calculate R plus by R minus. Radius of cation and radius of anion is given, and find out if this ratio belongs to, is 0.4. Suppose it is 0.4. Then 0.4 comes in this range, 0.225 to 0.414. Then definitely that is tetrahedral. If it is 0.52, then it belongs to this region. Then it is octahedral arrangement. This way you can solve the problems and predict the structural arrangement. Okay, thank you.